Dear students, now we are going to discuss single step matching and its derivation. Impedance matching is an important concept which is mainly used to provide maximum power transfer in high frequency transmission line. There are two types of step matching available. One is single step matching, the next one is double step matching. What is mean by step? It is an appropriate length of a short circuited or open circuited line. Okay. So in this video lecture we are going to analyze single step matching. So in this method we are going to use single step line of suitable length which is connected in parallel at a designated distance. That means at a proper distance where we can get the real part of the source impedance is equal to the characteristics impedance. So whenever the source impedance is equal to the characteristics impedance, then we can achieve the impedance matching between source characteristics impedance and receiver impedance. Do you all understand this concept? Then only we can transfer the maximum power from source to destination. In this single step matching, we have to consider two important parameters. One is the location of the step, the next one is the length of the step. So here the location of the step means that is a designated distance where we can get the source impedance is equal to the characteristics impedance and also the length of the step. Do you all understand this concept? So that's what given here. An open or closed single step line of suitable length is shunted at a designated distance at which the real part of the source admittance is equal to the characteristics admittance. Here we can say that as the source impedance is simply equal to the real part of the characteristics impedance R naught. So the line from the source to this point is known as the smooth line. So here in this we are using the term admittance because we are going to analyze the maximum power transfer. That's why we are using admittance instead of impedance. Okay. Next we are going to derive the location of the step and length of the step using reflection coefficient. So for that we can consider the input impedance of the transmission line. We have already derived this value in the input impedance lecture video. You can refer that video. Okay. So here we are going to use that formula as such. The input impedance is denoted as Zi, that can also be represented as Zs, that is equal to Z0 into 1 plus k e power minus 2 gamma L divided by 1 minus k e power minus 2 gamma L. So consider this as the first equation. So in this one, k is nothing but the reflection coefficient. As we all know that for lossless line there is no attenuation. So alpha is equal to 0, gamma is equal to j beta. So here gamma is equal to what? Alpha plus j beta. Here alpha is equal to 0. Correct? So we can write gamma is equal to j beta and the k value can be represented as the modulus of k into e power j5. That is magnitude along with the phase. Consider this as the 2. So here we are going to substitute the values of 2 in this first equation. Then we can get Zs is equal to Z0 into 1 plus k e power j5 e power minus j 2 beta L. Here k can be replaced with that value magnitude of k into the phase e power j5. Here gamma is replaced with the value j beta. Okay. So in the next step we are going to take this e power j as a common one. Then we can write Zs is equal to Z0 into 1 plus modulus of k e power j of 5 minus 2 beta L. The same way we can write in the denominator 1 minus modulus of k e power j 5 minus 2 beta L. Do you all understand this concept? So for further simplification, what we are going to do? We are going to consider the admittance value. As I told you earlier, so analyzing the circuit using admittance is a simple method. So here we can take Ys is equal to 1 by Zs. Admittance is the reciprocal of this impedance. So here we can take Z0 is nothing but what? Z0 is equal to R0, correct? The real part of the characteristics impedance 1 by R0 is equal to the conductance G0. Okay, so here we can say 1 by Z0 is equal to G0. Then this expression can be written like this: Ys is equal to G0 into the numerator becomes denominator, denominator becomes numerator. So we can take 1 minus k into e power j of 5 minus 2 beta L divided by 1 plus k e power j 5 minus 2 beta L. In the next step, we are going to expand this formula as we know that e power j theta is equal to what? Cos theta plus j sin theta. So here we are having theta as 5 minus 2 beta L, okay? Then we can get Ys is equal to G0 into 1 minus k into e power j5 minus 2 beta L can be written as cos 5 minus 2 beta L plus j sin 5 minus 2 beta L. Similarly, in the denominator 1 plus k cos 5 minus 2 beta L plus j sin 5 minus 2 beta L. So in the next step, we have to multiply this k inside this bracket. Then we can get Ys is equal to G0 into 1 minus k into cos 5 minus 2 beta L minus jk sin 5 minus 2 beta L. The same way we can multiply in the denominator 1 plus k cos 5 minus 2 beta L plus jk sin 5 minus 2 beta L. So in this expression, we can have the complex term in the denominator. In general, we do not want this complex term in the denominator. For that, we are going to multiply the numerator and denominator by the complex conjugate of this denominator value. So complex conjugate means we are going to multiply the numerator and denominator with the value 1 plus k cos 5 minus 2 beta L minus jk sin 5 minus 2 beta L. Do you all understand this concept? So whenever we are going to multiply the numerator and denominator with the complex conjugate of this denominator value, in this denominator we are going to get a squared plus b squared, correct? So here a plus jb into a minus jb is equal to what? A squared plus b squared. The same concept in this denominator. We can take this 1 plus k cos 5 minus 2 beta L as a. Here it is plus jk sin 5 minus 2 beta L. Here it is minus jk sin 5 minus 2 beta L. So this term, this denominator can be written like this. So here we can get 1 plus k. There is no square term here. 1 plus k cos 5 minus 2 beta L the whole square plus b is k squared sin squared 5 minus 2 beta L. So in the same way we can consider this numerator. Here this 1 minus jk sin 5 minus 2 beta L. In the second term we can have the same term 1 minus jk sin 5 minus 2 beta L. Here it is minus, here it is plus. We can simplify the term like this: 1 minus jk sin 5 minus 2 beta L the whole square minus k square cos square 5 minus 2 beta L. Then we can simplify all the terms. We can get the answer as G0 1 minus k squared sin squared 5 minus 2 beta L minus 2jk sin 5 minus 2 beta L minus k squared cos squared of 5 minus 2 beta L. Same way we can expand this term also, okay? This numerator we can have this term as minus k squared sin squared 5 minus 2 beta L. Here it is also minus k squared cos squared 5 minus 2 beta L. So we can take this minus k squared as a common one. Then we can get sin squared plus cos squared. So we can write this term as 1 minus k squared and this term minus 2jk sin 5 minus 2 beta L. Here it is plus k squared. Here it is plus k squared. We can take it common one. Then we can get cos squared 5 minus 2 beta L plus sin squared 5 minus 2 beta L. That value is 1, right? So 1 plus k squared plus 2k cos 5 minus 2 beta L. You all understand this one? In the next step, we can get the source admittance is equal to G0 into 1 minus k squared minus 2jk sin 5 minus 2 beta L divided by 1 plus k squared plus 2k cos 5 minus 2 beta L. Okay? As we all know that the source admittance is equal to conductance plus the imaginary part of the susceptance. So here we can say Z is equal to what? RS plus JXL. The reciprocal of this ZS is nothing but YS equal to 1 by RS is nothing but GS plus JXL or XS. Okay, that can be written as yes, that is susceptance. Okay, so here YS is equal to GS plus JSS. If we are going to normalize this term, normalize means what? We are going to divide all the terms with its characteristics value. So here Ys by G naught is equal to Gs by G naught plus JSS by G naught. This is the normalized value. So we are going to move this G naught to this side to get the normalized source admittance. Then we can get Ys by G naught is equal to 1 minus k squared minus 2jk sine phi minus 2 beta L divided by 1 plus k squared plus 2k cos phi minus 2 beta L. This term can be written as the real part and imaginary part. So here this denominator is common for real as well as imaginary. So 1 minus k squared by this denominator value. Here it is minus, right? So minus j 2k sine phi minus 2 beta L divided by this denominator. So it is in terms of real and imaginary. In the next step, we are going to equate the real parts as well as imaginary parts of these two expression. So then we can get equating the real parts, we can get Gs by G naught is equal to what? 1 minus k squared by 1 plus k squared plus 2k cos phi minus 2 beta L. Consider this as the third equation. Next, we are going to equate the imaginary parts, that is susceptance by G naught. The normalized susceptance value at the input side is equal to minus 2k sine phi minus 2 beta L divided by 1 plus k squared plus 2k cos phi minus 2 beta L. Consider this as the fourth equation. From these two equations, we are going to get the location and length of the stub. Okay. Now we are going to find out the location of the stub. It is denoted as LS or distance D. As we all know that at the location of the stub, the characteristics impedance is equal to the source impedance for matching purpose. So we can say the conductance at source is equal to the characteristics conductance. So here the condition is what? The location is equal to LS. From the third equation, we can say this GS by G naught is equal to what now? It is equal to 1 because both are equal. Okay. Then we can write the third equation as 1 minus k squared by 1 plus k squared plus 2k cos phi minus 2 beta Ls is equal to 1. So in this formula, we can write L as Ls. That is the location of the stub. At that position, the Gs is equal to G naught. Okay. Then we can cross multiply this value. We can get the value as 1 minus k squared is equal to 1 plus k squared plus 2k cos phi minus 2 beta Ls. Okay. So here this one as well as this one both can be cancelled. We are going to move this k square to this side as minus. Then we can get 2k cos phi minus 2 beta Ls is equal to, this becomes minus in this side. That means minus k squared that is equal to minus 2k squared. Okay. So in this one, this 2 as well as this 1k and this 1k both can be cancelled. Then we can get cos phi minus 2 beta Ls is equal to minus k. Consider this as the fifth equation. This is very important. Okay. Next step, we are going to move this cos to this side as cos inverse because we are going to find out the value of this Ls. Okay. So here it becomes cos inverse of minus k. As we all know that cos inverse of minus theta is equal to what? Minus pi plus cos inverse of theta. So here theta is nothing but what? K. Okay. Then we can write this right hand side as minus pi plus cos inverse of k. Consider this as the sixth equation. Okay. In the next step, we can take this minus 2 beta Ls to this side as plus. So this term becomes what? Plus 2 beta Ls. At the same time, we can move this minus pi plus cos inverse k to this side. So here it becomes what? Phi. This minus becomes plus pi minus cos inverse of k. Okay, we want to find out this Ls. So we can write this term like this. 2 beta Ls is equal to phi plus pi minus cos inverse of k. Okay, from this we can get the value of this ls by moving this 2 beta to this side as a denominator. Okay, as we all know that beta is equal to 2 pi by lambda. We can substitute that value in this formula. Then this term becomes 4 pi by lambda. Then finally we can get the location or position of the stub as ls is equal to lambda by 4 pi 5 plus pi minus cos inverse k. So here it is very important formula. By using this formula we can solve some problems. If we know the values of reflection coefficient k and the lambda, we can find out the location of the stub. Okay. So next we are going to derive the length of the stub, that is denoted as LT. For that we can use the fourth equation, that is the normalized susceptance SS by G naught is equal to minus 2k sin phi minus 2 beta ls divided by 1 plus k square plus 2k cos phi minus 2 beta ls. So from this fifth and sixth equations, this cos phi minus 2 beta ls can be written as minus k. Here this phi minus 2 beta ls can be written as minus pi plus cos inverse of k. So these two are very important equations, that is fifth and sixth equations. We are going to substitute these two in this expression. So here we can write minus 2k sin phi minus 2 beta ls is written as minus pi plus cos inverse of k. Here cos of phi minus 2 beta ls can be written as minus k. Then we can simplify this term like this. So here as we all know that sin of minus pi plus theta is equal to what? Minus sin theta. So here theta is nothing but cos inverse of k. So here sin of minus pi plus cos inverse of k can be written as minus sin cos inverse of k. Minus into minus plus. Okay. So here in this denominator we can get 1 plus k squared. Here plus into minus minus 2k squared, right? So next for further simplification we can consider cos inverse of k is equal to theta. Then k is equal to cos theta, correct? So here sin of cos inverse of k is equal to sin cos inverse of k is nothing but theta. It can be written as square root of 1 minus cos square theta. Sin theta is equal to what? Square root of 1 minus cos square theta. Cos square theta means k square. So in this expression we are going to write sin of cos inverse of k as square root of 1 minus k square. Do you all understand this one? It can be written like this. The normalized susceptance SS by G naught is equal to 2k. The sin of cos inverse k can be written as square root of 1 minus k square divided by 1 minus k square. This 1 minus k square can be written as square root of 1 minus k square into square root of 1 minus k square. We can divide these two values, right? Then we can get the value as 2k divided by square root of 1 minus k square. So here we can move this G naught value to this side. So here the susceptance is equal to G naught into 2k divided by root of 1 minus k square. As we all know that the susceptance of the stub in transmission line is G naught into cot beta LT. So this LT is nothing but length of the stub. The susceptance depends on what? The length of the stub. Do you all understand this concept? So this is the susceptance of the stub. Okay. So here we can simply cancel these two values. We can get cot beta LT is equal to 2k by square root of 1 minus k square. Okay. So cot is nothing but 1 by tan beta LT. So we are going to find out the value of this LT, right? So we have to take the reciprocal term on both the sides. Then this term can be written as tan beta LT is equal to, here we can simply take the reciprocal. So square root of 1 minus k squared by 2k. Do you all understand this concept? So from this we can get the value of this LT. So here we can move this tan to this side as tan inverse. So beta LT is equal to tan inverse of square root of 1 minus k squared by 2k. Then we can move this beta to this side, that is 1 by beta. So as we all know that beta is equal to 2 pi by lambda, we can write 1 by beta as lambda by 2 pi. Then the length of the stub LT is equal to lambda by 2 pi tan inverse of square root of 1 minus k squared by 2k. Okay, do you all understand this formula? This is very important expression. We are going to find out the length of the step using this formula. Okay, so here the location of the step and the length of the step both can be determined if the reflection coefficient and the frequency values are known. So here the reflection coefficient k is equal to s minus 1 divided by s plus 1, where s is nothing but the standing wave ratio. Okay. In real-time applications, we prefer only the short-circuited step. The advantages of short-circuited step over open-circuited step are given here. The short-circuited step is simple and easy to design. It can be established with a large metal plate, so the radiation loss is very less. Okay, it provides lower radiation loss. But there are some limitations of this single step matching. This single step matching is applicable only for single frequency. If you want to use it for multiple or variable frequency, then the location of the step has to be varied. It is very difficult to vary the location of the step. Okay, there are two adjustments required, the length as well as position of the stub. Okay, then it is possible only in a open wire line. In case of coaxial line, it is difficult to locate the stub at exact point. So these all are the limitations of single step matching. That's why we move on to the double step matching.